Hello dear students, this is Professor Onindo Das from Achievers and welcome to my lecture series on chemical equilibrium. So this is our 7th lecture. Here we will understand the relationship between equilibrium constants, reaction quotients and Gibbs free energy. That means in this particular lecture we will deal with the thermodynamics of chemical equilibrium. So this is a very important lecture. Here we will be dealing with the fundamental thermodynamic aspects of chemical equilibrium. This is a very important chapter, okay, or lecture rather. So first of all, let us list down the important equations. So I will start with thermodynamics of chemical equilibrium. So the fundamental equations. We'll list down the fundamental equations. Please note that we will not deduce these equations in this context because that is beyond the scope of our syllabus. We'll just know the equations. Okay. So the very first equation is delta G0 is equal to minus RT ln K equilibrium. Delta G0 refers to the change in Gibbs free energy at the standard state. Delta G0 refers to the change in Gibbs free energy at the standard state. At standard state, what is standard state? At standard state, active mass of any component is unity. Okay. At standard state, active mass of any component is unity. If the standard state is defined with respect to pressure, then we define it at 1 atmosphere pressure. The standard state is, at standard state, P is equal to P naught equal to 1 atmosphere. And if we define it with respect to concentration, then C equal to C naught equal to 1 molar. So this is the concept of standard state. If we define the standard state with respect to pressure, then at standard state the pressure is equal to P naught equal to 1 atmosphere. If we define it with respect to concentration, then at standard state it's the concentration is 1 molar. And the change in Gibbs free energy at standard state is known as G naught. So this is the expression, and we know that delta G naught is equal to minus RT ln K equilibrium. See, this K equilibrium is solely a function of temperature, and this G naught is also a function of temperature only. Change in Gibbs free energy at standard state is a function of temperature only. Why? There are two different logics. If you ponder into this equation, then you can say that K equilibrium is only a function of temperature, and you have only one variable, that is temperature. So necessarily delta G naught should be a function of temperature only. So from here you can make an interpretation. You can make another interpretation in this manner. You see, delta G, that is change in Gibbs free energy, not at the standard state, but generalized change in Gibbs free energy. It depends on temperature, pressure, and composition. It will depend on everything. Now, if we are looking for standard state, then what is happening? At standard state, P is equal to P naught equal to 1 atmosphere. The compositions refer to unit active masses. That makes delta G, which is now equal to delta G naught, to be a function of temperature only. Initially, delta G was a function of temperature, pressure, and composition. But when you are getting reduced to the standard state, then you are having the pressure reduced to 1 atmosphere, and all the active masses are reduced to unity. So the pressure and composition becomes affixed at unity. So naturally, the only variable parameter left out is temperature. So delta G happens to be a function of temperature. Delta G0 rather happens to be a function of temperature only. So I think you have understood this equation. Now my second equation is about delta G. Delta G is equal to delta G naught plus RT ln Q. Now we know everything about the functionalities. Delta G, it's a function of temperature, pressure, and composition. Delta G naught is just a function of temperature. So what about Q? We know that at equilibrium, Q becomes KQ. We know that. We have already studied that. So if Q becomes KQ, it is a function of temperature only. So Q is obviously a function of temperature because Q is more generalized in context to KQ. So if Q is the more generalized picture of KQ and KQ is a function of temperature, then Q must be a function of temperature. Other than that, it has got a pressure dependent term coming from delta G. So it's a pressure dependent term is there, and a composition dependent term again coming from delta G. In the first term, delta G0, there is no composition dependence. RT is also a function of temperature, so it has got no composition dependence. So the pressure and composition dependence in the left hand side should always be borne in the right hand side of the equation. That's what equations are all about. The left hand side should be exactly identical to the right hand side. So if the left hand side is a function of temperature, pressure, and composition, the right hand side has got to be a function of temperature, pressure, and composition. Now, the first term is not a function of pressure and composition. In the second term, the coefficient RT is also not a function of pressure and composition. So Q ought to be a function of pressure and composition. And Q is again a function of temperature. Why? Because Q is the generalized case of equilibrium constant. And if equilibrium constant is a function of temperature, then by simple logic, Q has to be a function of temperature. So like G, Q is also the function of all the three parameters: temperature, pressure, and composition. I think all of you have understood this. Now let's move on to the third one. The third one is a combination of these two equations. This delta G equal to, you see, in place of delta G0, you plug in this particular result, minus RTLN KQ, and already you have got one RTLN Q. So obviously delta G becomes RTLN Q by KQ. So these are the important equations pertaining to thermodynamics of chemical equilibrium. And this interpretation was made by Van 't Hoff. And these are the Van 't Hoff equations. Okay. So these are the important Van 't Hoff equations. I think all of you understood this. Now we'll make some important interpretations with respect to the final equation, delta G equal to RTLN Q by KQ. As delta G is equal to RTLN Q by KQ, so one can say that if Q is less than KQ, then what is going to happen? If Q is less than KQ, then this particular parameter Q by KQ is less than unity. And we know that ln1 is 0. ln of something less than 1 must be negative, and ln of something greater than 1 must be positive. So if Q is less than KQ, then ln Q by KQ is negative. And this particular term, RT, this is always positive. Kelvin temperature is always positive. R is always positive. So naturally RT is always positive. So this positive term multiplied by negative term, so delta G becomes negative. If delta G is negative, then the forward reaction becomes feasible. So in this case, the forward reaction will be feasible. If Q is equal to KQ, then what is going to happen? If Q is equal to KQ, then what is going to happen? In that case, ln Q by KQ is equal to 0. Why? Because Q by KQ is 1, ln 1 is 0. If this is 0, 0 multiplied by anything is 0. So delta G becomes 0. And that refers to the state of equilibrium. On the other hand, if Q is greater than KQ, then what is going to happen? Then Q by KQ is greater than unity. ln of something greater than unity is positive. So this positive multiplied by positive becomes positive. So delta G becomes positive. And if delta G is positive, then obviously it will favor the backward reaction. Okay. Now, let us make a plot of G with respect to time. So, here you have reactants and here you have products only. With time, the reactant is going to get converted into product. Okay. Here reactants only, and here products only. And let us replace the time axis by reaction coordinate. Reaction coordinate is nothing but the time axis. Reaction coordinate is a time dependent axis, but we are naming it in a different manner because we are basically converting the time axis or evolving the time axis into a more pertinent or into a more scientifically pertinent axis. That is the reaction coordinate. Because along this coordinate, the reaction will take place. It is also called advancement factor of the reaction. Okay. Now, if we do so, then what is going to happen? Say at this point, equilibrium is attained. So before equilibrium, G is decreasing, delta G is negative, Q is less than KQ. At equilibrium, G is minimized. At equilibrium, G is minimized. This stands for equilibrium. And beyond equilibrium, delta G is positive. What does that mean? That means the backward reaction becomes visible. Here Q is greater than KQ. And at this point, at equilibrium, Q is equal to KQ. So everything is tending to this point. This is the most stable point where G is minimized. Delta G is becoming equal to 0. I think all of you have understood these important concepts. Okay. Now, next we want to see the nature of temperature dependence of equilibrium constant. How does equilibrium constant depend on temperature? How does equilibrium constant depend on temperature? For that, we need to develop the fourth equation. We have already done 3 equations. Now we need to develop the fourth equation. The fourth equation is dln k equilibrium dt equal to delta H naught by RT square. This is done at constant pressure. dln k equilibrium dt equal to delta H naught by RT square. This is the expression. This is the differential form. This is the differential form. Now we will develop the integrated form, but we'll make some approximations. We will consider delta H naught to be independent of temperature. We will integrate under this approximation. Delta H naught may also be a function of temperature. In that case, the interpretation would become very complex, and that is beyond the scope of your syllabus. So we will not study that. We'll just confine ourselves to delta H naught independent of temperature. If delta H naught is independent of temperature, then delta S naught is also independent of temperature. That can also be proved thermodynamically, but I am not getting into that. Just remember, we are imposing a condition that delta H naught is independent of temperature. And if delta H naught is independent of temperature, then thermodynamically you can also establish that delta S naught is even temperature independent parameter, but we will not go into that mathematical interpretation. Just we will keep this thing in mind. If delta H naught is independent of temperature, then the approximation of delta S naught being independent of temperature is valid as well. Okay. So this is the approximation. Now let us integrate. If we integrate both sides, we get ln kq equal to minus delta H naught by RT plus some integration constant C. Now we need to find out the value of C. This is also very simple. You see, we have ln kq equal to minus delta H naught by RT plus C from here, and from the first equation we have ln kq equal to minus delta H0 by RT from the first equation. So from the first equation you can also write this to be minus delta G0 by RT. So minus delta H naught by RT plus C equal to minus of delta H0 minus T delta S0. We know that delta G is delta H minus T delta S. That is a very common equation. So delta G naught is delta H naught minus T delta S naught, or minus delta H naught by RT plus C equal to minus delta H naught by RT plus T will get cancelled out, delta S naught by R. So minus delta H naught by RT cancels out from both sides. So from here you can say C is equal to delta S naught by R. So from here you get ln kq equal to minus delta H naught by RT plus delta S naught by R. See, this is a straight line equation. Let me rewrite this equation once again. ln kq equal to minus delta H naught by R, just write it in this manner, multiplied by 1 by T plus delta S naught by R. Let us write it in this manner. Now, if we plot ln kq along y-axis and 1 by T along x-axis, then minus delta H naught by R must be the slope m, and delta S naught by R must be the intercept C. So from here, one can say that if we plot ln kq with respect to temperature, 1 by temperature, T to the power minus 1, then we are going to get a straight line. We are going to get a straight line. And a straight line can exist only in the first and the fourth quadrant. It will not exist in the second and the third quadrant. Okay. Why? Because T cannot be negative, so 1 by T cannot be negative. So, no question of second and third quadrant arises. The plot will exist only in the first or the fourth quadrant. Now, there are 6 options. With delta H0, delta S0. Both positive. Delta S0 negative, delta H0 positive. Both negative. Positive, negative, negative, negative. Okay. Let me generalize this. Let me generalize this a bit more. So delta S can be positive, negative, or 0. But in all these 3 cases, delta H naught can be positive. Again, delta S can be positive, negative, or 0. In all these cases, delta H naught is negative. Again, delta H can be positive, negative, or 0. In all these cases, delta H naught is 0. So there can be 9 options, 9 combinations. There can be 9 combinations. For positive delta H naught, that is for endothermic reaction, if delta H naught is positive, then the reaction must be endothermic in nature. So for endothermic reaction, you have 3 options, delta S naught plus, minus, 0. For exothermic reactions, again you have 3 options. And for isoenthalpic reactions, where delta H naught is 0, again you have 3 options. Okay. Theoretically, there are 9 options. So for positive delta S naught, that is this one, and this one, you can have delta H naught positive. If delta H naught is positive, then there is a negative sign in front, so the slope becomes negative. So this is endo. This is for endo. For isoenthalpic, delta H naught is 0. If delta H naught is 0, then the slope is 0. Slope 0 means it's parallel to 1 by t axis. And for exo, what is going to happen? For exo, delta H is negative. Delta H naught is negative. Negative multiplied by negative is positive. So this is going to happen for exo. Same thing is going to happen for negative delta S. Again, you have three options. Exo, iso, endo. And for 0 delta S, again you have same three options. Exo, iso, endo. So these are the 9 possible options. Okay. Now, had you integrated this with limit, if you have integrated this with limit, then what would have happened? dln kq equal to delta H0 by R dt by t square. So at temperature T1, it's KQ1, and at temperature T2, it's KQ2. Initially, we have integrated the differential equation indefinitely, and we have obtained an expression. From there, we have obtained the plots and all. Now, if we had integrated it definitely, then let us consider that at a temperature T1, equilibrium constant is KQ1, and at temperature T2, it's KQ2. Because KQ is temperature dependent parameter. Then what you can say? You can say that ln KQ2 by KQ1 equal to delta H0 by R multiplied by minus 1 by t. There is minus 1 by t coming. So, you have a minus 1 by t term, T1 and T2. Upper limit is T2, lower limit is T1. So, if you substitute it, you will get ln KQ2 by KQ1 equal to delta H0 by R multiplied by 1 by T1 minus 1 by T2. So this will be the expression. Very simple expression. Okay. So we are studying the nature of dependence of equilibrium constant with temperature, and we have got it. For exothermic reaction, what is happening? For exothermic reaction, what is happening? You see, for exothermic reaction, in this direction, 1 by t is increasing. That means t is decreasing. Now ln K equilibrium is increasing. That means K equilibrium is increasing. So with lowering of temperature, the equilibrium constant will increase. If you lower the temperature, KEQ increases. Okay. With lowering of temperature, the equilibrium constant increases. And what is equilibrium constant all about? In equilibrium constant, you have product in the numerator and reactant in the denominator. So if equilibrium constant increase, then product increases, reactant decreases. That means the forward reaction is favored. That's what we have done in our previous lecture. So this favors the forward reaction. So lowering of temperature favors exothermic reaction. Done. Done. So for endothermic reaction, you don't have to interpret. The reverse thing is going to happen. That means with increase in temperature, KQ is going to increase. That means increase in temperature is going to favor the forward reaction. So all the endo processes are done. Now what about the iso processes? Iso processes are trivial. These are trivial. Why trivial? You see, if you vary temperature, there is no change in equilibrium constant, it is parallel to the x-axis. That means if delta H0 is 0, that means for isothalpic process, equilibrium constant is not a function of temperature. It is independent of temperature. So increase or decrease of temperature has no effect. For exothermic reaction, decrease of temperature favors forward reaction. For endothermic reaction, increase of temperature favors forward reaction. But here, K equilibrium is independent of temperature, and as K equilibrium is independent of temperature, being independent of temperature, what is going to happen? There will be no effect of variation of temperature. So for isothalpic reaction, no effect of temperature. No effect of variation of temperature. So we have understood this. So these are some very important fundamental concepts that we have already understood. Now we will get into some important problems. Some important problems in context to equilibrium constant. Some important problems in context to equilibrium constant. Let's get into that. What are those problems? In the previous lecture, I have told what is the effect of stoichiometry. What is the effect of stoichiometry? But it was not discussed in a detailed manner. So now we'll discuss the effect of stoichiometry in a detailed manner over here. Okay. So suppose this reaction in general is multiplied by a factor gamma, and it becomes gamma AA, gamma BB, gamma CC plus gamma DD. And here In this case, if the equilibrium constant is KEQ1, and in this case the equilibrium constant is KEQ2, then how can you relate these two equilibrium constants? This is my first problem. And my second problem is, say there is a series of reactions, R1 in equilibrium to R2, R2 in equilibrium to say R3, R3 in equilibrium to say R4, say Rn minus 2 in equilibrium to Rn minus 1, Rn minus 1 in equilibrium to Rn. Rn in equilibrium to say Rn plus 1. So let's there be n number of reactions. First, second, third, this is the nth reaction. If you add all the reactions together, what will you get? You will get R1 in equilibrium to Rn plus 1. Now, if all these equilibrium constants are K1, K2, K3, Kn minus 2, Kn minus 1, Kn, then what is the overall equilibrium constant, expression of overall equilibrium constant in terms of K1, K2, K3, Kn minus 1, Kn minus 2, Kn, in terms of all these things, how can you develop the expression of K? So these are the two important problems. If you know the way how these problems are solved, you can solve any equation. Okay. So let's move on to the solution of the first problem at first. We'll use some important concepts of thermodynamics over here. We know that G is extensive in nature. And if any thermodynamic quantity is extensive, it is also additive in nature. This is known to all of us from the fundamentals of thermodynamics. So if G is additive, then delta G02 should be gamma times delta G01. If G is additive, then multiplying gamma to a particular reaction has this effect on delta G0 because G is additive. If you multiply a reaction by gamma, then delta G0 has to be multiplied by gamma because G is additive in nature. So this is minus RT ln K2. Let us write K equilibrium 2 as K2 for simplicity and K equilibrium 1 as K1 for simplicity. So minus RT ln K2 equal to gamma times minus RT ln K1. We have used the expression delta G0 equal to minus RT ln KQ. Now minus will cancel out, RT will cancel out. And this gamma will go to the power of K1 from the fundamentals of logarithm. So ln K2 is equal to ln K1 to the power gamma. From the basic concepts of logarithm, basic laws of logarithm, we can write this. So therefore, K2 must be K1 to the power gamma. So if you multiply a reaction by a scalar factor, then that scalar factor goes to the power of the initial equilibrium constant in order to obtain the final equilibrium constant. Simple, understood? Done? Now let us move on to the final problem. What about this series? Here also we will use the additive nature of G. That means we will say the overall change in Gibbs energy delta G0 at standard state should be equal to sum of the individuals delta G01 plus delta G02 plus delta G03 up to delta G0n. Delta G0 is minus RT ln K equal to minus RT ln K1 minus RT ln K2 minus RT ln K3 and so on minus RT ln Kn. Just substitute the values. Now minus RT terms will get cancelled out. So ln K becomes ln K1 plus ln K2 plus ln K3 up to ln Kn. Now applying the laws of logarithm, one can say that ln K1 plus ln K2 plus ln K3 up to ln Kn is ln of K1, K2, K3 up to Kn. Now again if you take antilog, you get K to be equal to K1, K2, K3 up to Kn. That means the overall equilibrium constant is the product of the individual component equilibrium constants. You just take the product, you will get the overall equilibrium constant. So that's all students for this particular lecture. See you in the next lecture. Bye.